Haloalkanes are another important group you need to know about. Now the halogens are in group 17, and typically the halogens we'll be talking about will be the chlorine, bromine or fluorine. Now naming them is fairly easy. The chlorine is obviously here, that's in the number 1 position in terms of we give it the lowest possible number. So that would be 1-chloro, and because there are 4 carbons it would be called butane. Is it primary, secondary or tertiary? Well, we look at the carbon that the chlorine is attached to and count how many other carbons. There's only one, so this would be a primary haloalkane. Okay, now another one would be this bromine attached to these 2 carbon or ethane. So this is 1-bromo ethane. Okay. And that too would be a primary haloalkane because it's only attached to 1 other carbon. Here we have the bromine attached to the carbon which has got 2 others, so that would be a second degree haloalkane, and this one's name would be 2-bromopropane. 2-bromopropane. Okay, so now on to the properties. Okay, if we look at the properties of this and we consider melting point and boiling point, what kind of bonding is present here? Well, there's always going to be temporary dipole bonding. That's almost a given on, well, it is a given on every single molecule. Is there any other kinds? Now, if we look at the chlorine here, that's going to be slightly more electronegative than the carbon. So we will get a permanent dipole bond here. So if we're arranging these in order, we would say that haloalkanes are greater than, say for instance, just normal alkanes. But if we compare them to, for instance, alcohols, they would be less than those because of the ability of alcohols to hydrogen bond. So whenever we're talking about bonding, we talk about the amount of energy it takes to break the bond. If it takes a large amount of energy reflected in the boiling point or melting point, then what that tells us is bonding must be correspondingly strong if it's a strong melting point, or low if it's a low melting point, for instance. Solubility. Well, you may consider the fact that it's got a permanent dipole, that this is probably a polar molecule, and that it's probably going to be soluble. It's not that much of a dipole though, and with the other carbons and hydrogens present in some of the longer chains, or even some of the shorter chains, it tends to be insoluble in water. So it's insoluble, and it's considered basically to be overall non-polar. Okay, so it's not going to mix with water too well. Now the reactions of the haloalkanes, and really this, in a way, if you're trying to memorize it, just comes down to 2 things: KOH or NaOH in aqueous and alcohol, and the second, which I'm not showing on this page, which is basically reacting with NH3, or which is ammonia or another amine. And when that happens, we basically get a amine substituting on there. But let's have a look at this. So the aqueous conditions are very important, and you must mention them. That this is a substitution reaction, and again that's just something that you should know, because we're substituting the halogen. In this case it's a bromine right here, and we're going to be replacing it with a OH. So from here, if you do not mention aqueous conditions, you will not get this marked right. Now, you can either have KOH aqueous or NaOH aqueous. In either case, this should work. Okay. So on the other side, obviously, you're just going to be swapping out that, and the Br comes off, and you would get plus KBr, but we're not going to worry about that too much. It's the main product that we're interested in. And so that's an important one, the substitution one. Now this one is an alcohol, so if you have KOH in ethanol or KOH in alcohol, it's the same thing, or you have NaOH in alcohol, it's the same as NaOH in ethanol. So this is an elimination reaction, and what's going to happen here is the halogen, the Cl, is going to be eliminated, and either this H or this H next door. So how do we decide on this? Well, this carbon has got 2 H's, and this carbon has got 3 H's. Remember, it's a pore that gets poorer. So I'll just say complete this KOH ethanol, and that's going to go to 1, 2, 3, 4 carbons, and because that's got a fewer number of H's and it's with elimination reactions, it's the pour that gets poorer, it's the opposite of the addition reactions. We're going to get the major product with a double bond there. Now just for clarity at this stage, I will leave off the H's, and then on the other one we're going to get a double bond on the other side between these two, or between these two carbons. So there we go, and that's going to be there. So I'll actually just leave off the H's altogether. So you get the major and the minor. So it's an important one to remember. Conditions matter. Okay. Now, it's a substitution reaction with ammonia, and again the conditions matter. It's an alcohol. If it's not an alcohol, then we'll probably get an OH coming in here and substituting this pretty much like the KOH aqueous or the NaOH aqueous, because NH3 is a base as well. So I've just drawn this out in a little bit more detail here, because what's going to happen is it's going to come in here and bond here. The Cl is going to be removed, and it's important to realize that only 3 things generally will bond to a nitrogen. So one of these H's basically disappears, or it doesn't really disappear, it forms HCl on the other side because the Cl gets removed, and that means on this side we're going to end up with NH2. So there's one less H. So because in order for the nitrogen to bond to the carbon, one of the H's has to go. Okay. Now what I'd like you to see in the next reaction is how similar this next reaction is. Now this really is the same reaction, it's just we've got a slightly longer, instead of being NH3, it's NH2, and a methyl group is bonded. Effectively, this methyl group here has bonded to the ammonia, and one of the H's is gone. But anyway, so when this goes in and substitutes there, one of the H's is going to go, because again the nitrogen can only really bond to 3 things. So the product's going to end up being 3 carbons, and we'll have the, sorry, just must drew that wrong, we'll have NHCH3 bonding to that, and then we just fill in the rest with H's. Okay, so if you start to see some of the similarities, that really helps. If we were to look at this in a summary, the reactions for haloalkanes is this KOH and aqueous, or NaOH and aqueous. We're basically just swapping the ClBr for an OH group. KOH and alcohol, or NaOH and alcohol, we're eliminating or removing a Cl or a Br, plus an H next to it. Remember the pour get poorer, so the H gets removed from the carbon next to it, which has got the fewest amount of H's. Pour gets poorer. And that forms a double bond. And then we've got these substitution reactions where basically we're swapping a halogen, so we're swapping a Cl or a Br, potentially an F, I guess, or they're not commonly used in exams. I'm going to be swapping it for an NH3, which once it's bonded, it's going to be NH2, because nitrogen can only bond to 3 things, or something like CH3NH2. This could be potentially longer, and go to CH3NH when it's actually bonded, remembering it's the nitrogen itself which is bonded to the carbon of, that's replacing the chlorine. So you're putting that there. Okay, and that's haloalkanes.